Hey. Wrong class? Yeah. I've had days like that. All right. We're talking about implementing a generic data structure. So a data structure that can hold elements of some unspecified type, I guess, or of any type. So we're implementing a generic stack. Now to do this, we have to change the way our node structure works. Right. So instead of holding an element of type int or some other type, right? So our current stack holds an element type int. We're now going to hold a pointer of type void, right? So a pointer to void. Now remember, a pointer to void can point at any object, right? So this is what gives us our ability to implement a generic stack. If you look at the stack implementation, you'll see quickly that there are functions that don't need to change, right? So initializing a stack, nothing special needs to happen. Right? Checking if a stack is empty or asking for the size of a stack, there's nothing that needs to change. Right? So that's good. Some functions need a very small modification to them. Right? So for example, when I push an element onto a stack, right? Instead of pushing an int element onto the stack, I'm now going to push a pointer to an element on the stack. Right? Where the pointer is a void pointer. Similarly, when I pop an element from the stack, I'm not going to return an int. Right? I'm now going to return a pointer to an element, right? Where again the pointer type is a void pointer. Now, when you look at the printing function, so when you print a stack, there's a more serious problem. So let's look at that. And I probably closed it. Yeah, I probably. Sorry about this. I should have had this ready. Stack. No, stack. Where are the stacks? Sorry, I forgot where I put them. That's not right. I don't want the generic one. Oh, all right. Oh, wait, it's elf stack, right? Linked list, okay. So up into linked list, L stack. All right, so when we, oh wait, is it here? Where's print? Free, I guess print's not here. Sorry about this. Where's the linked list one instead? Okay, what about the linked list one instead? Because they're all going to work the same. Is it not here either? How come I don't have a print function? One of these has a print function. L stack, no. Wow, this sucks. Okay, hang on, let me do it this way. Get rid of that, and go to here. Is this the void? This is void, okay. Okay, so I'm going to pretend. Oh, this is for a, okay, never mind. I'm a dummy. Here's a print function that works for an int stack, right? So this is iterative version of print for an int stack. All right, so in the, when you print a stack, right, again, it's a node-based stack, so we're going to start by pointing at the top node, and then we're just going to loop over the nodes, printing nodes as we go. Right? Now when we print, I know that the element type is int. Right? So I can use printf and use %d to print the element type. But now I've got a problem, because when I change the element type to void star, right? So now I've got pointers to elements, right? I don't know how to print the element now, right? So next line works if elem is int or has type int, right? What what do I write if elem has type void star? Right, so now how do I print out the element? Right, so what do I put there to print out an element if the element type is unknown? Right, because you have to remember the stack doesn't know what the element type is. Right, all it knows is that there's some pointer, there's a void pointer that points at an element. Right, and so that's a problem. Right, and you have another problem as well. Right, so as the implementer of the stack data structure, you've got no idea how to print the element type because the user is the one that's specifying the element type, right? And this includes user-defined types such as structs, right? So in other words, the user can make their own structure and push, I guess, instances of their structure onto the stack, right? Now how do you print that out? Right? Similarly, freeing a stack has the same problem, right? So when we free a stack, we're going to free the elements, right? The problem is our elements now are pointers to something, right? And I also don't know, as the implementer of the stack, right? Does the user want me to free the elements when I free the stack, right? Because they're giving me pointers to elements, right? They're not giving me the elements themselves. They're giving me pointers to the elements. So when they push their elements onto the stack, right, they're giving me pointers to their elements. But when I clear the stack or when I free the stack, do they also want me to get rid of the elements or not, right? Now, if you just assume that the user wants you to free the memory associated with the elements, right, then you have no idea how to free the memory correctly, right? Because the element type can have any type, right? And that includes user-defined types like structs, right, which might need their own special treatment when you free the memory associated with the struct. Okay, so how do we solve this problem, right? So you can't move forward with this, so one compromise is to say, look, I can't print a stack. I can't give you a function to print a stack. You're going to have to write your own. Two, I can't give you a function to free a stack. You're going to have to write your function. You're going to have to write a function to free a stack on your own, right? Which would be okay, right? That's one decision you could make. But there is a way to do this, and there is a way to implement a stack so that you can free the element. You can provide a function that frees the elements of a stack, and you can provide a function that prints the elements of a stack, and you can provide functions that do anything else with a stack. Right? So, for example, you can write a function that tests if two stacks are equal, or does a stack contain a particular element, or so on and so forth. Right? All of these functions have the same problem. Right? If you want to check if two stacks are equal, you have to check if the elements of the stacks are equal. If I don't know what the element type is, I don't know how to check for equality. Right? So the solution is you can derive a solution by the following observation. Right? So printing an element or freeing an element or checking if two elements are equal, right? These are all described by an algorithm of some kind. Right? The user is able to supply that algorithm. Right? So the user knows how should they free an element. The user knows how they want to free an element. The user knows how they want to print out an element. The user knows how to test if two of their elements are equal to equality. If two of their elements are equal. Right? Now, how do you implement any algorithm? Well, you just implement a function. Right? So in C, you implement an algorithm as a function. Right? In Java, you implement it as either a method or as an object. Right? So that's how you do it in Java, and similarly, that's how you do it in Python. Python, you can also implement it as a function. So what you need here now is a mechanism to pass a function to another function. Right? So to print, if I have a stack print function, I can ask the user for a function that can print an element. Right? Inside my print function, I can then use their function to print the elements. Right? So that's the trick here. And so I need a mechanism that lets me pass a function to another function, and that mechanism in C is a pointer to a function. Right? So you can create a pointer to a function, and the way you do it is you write something that looks like this. So this is the generic form for writing a pointer to a function. Right? If I want to make a pointer to a function, then what you end up writing is something like, so You have a function, every function has a return type, possibly void, right? So the return type goes first, right? This is when you define your function to a point, sorry. Oh, sorry, here's your function, right? Return type, function name, right? List of parameters, right? Where each parameter has a name and a type, right? So that's what every function in C looks like. If you want a pointer to that function, then the way the pointer looks like is as follows, right? Now this is very weird. So the syntax is very strange because it doesn't look like a pointer, it doesn't look like a variable declaration, right? But believe it or not, this is a variable declaration, right? So sorry, this is a type, no, this is a variable declaration. That's, sorry. This could be, so this can be a variable declaration. So, return type, function name, parameters, right? The corresponding pointer looks like the return type of the function. That's the name of your pointer, right, with a star in front. It has to be inside brackets, right? So that's the name of your variable right there. Right? Brackets, right, the parameters of the function, right? So if you've got a function and you want to take a pointer to the function, what you do is you take the return type of the function, right? Write that there, right? You grab the parameter list of the function, and you write that there, right? And then you name your pointer, you write that there, right? And you put a star in front to indicate that it's a pointer, and put the whole thing in round brackets. Right? So strange, the very strange syntax. Right? So for example, pointer to func. Here it is. All right, so let's look at some. So we've got three simple functions here, right? We've got a slightly more complicated function here, because this one's slightly more complicated because it returns a pointer, right? Returns a pointer to double. And then we've got a fifth, very strange looking function here. Oops, sorry. How did I do that? Okay. So we'll come back to this one at the end, because this is the most complicated example, right? But do nothing is simple, right? Its return type is void, right? Its parameter list is void, right? Its name is do nothing, okay? And it does nothing, it just returns. So if I want to make a pointer to this function, right? So I want to make a pointer called pointer1 to the do nothing function, right? So you write the return type of the function, so that's void, right? I write the parameter list of the function here, right? And then I give the name of the pointer here, right? So this reads as pointer1 is a pointer to a function that returns void that has no parameters, right? I can make pointer1 point to the do nothing function by taking the address of the function, right? Which also looks weird, right? Because as you know, when you call the function, every time you call a function, you get a new version of the function. So what exactly is the address of this function? Who knows, right? You don't know until you actually run the program, until you actually call the function, right? But that's the syntax that you use. So let's look at the second one. So here I've got a function that returns void, right? It has a parameter list that's a single int. Right? If I want to make a pointer to this function, right? So pointer2, right? Then what you write is you write void, right? So that's the return type. You write in the parameter list here. Now, when you write the parameter list, you don't specify the parameter names, right? You only specify their types, right? And then you give the name to the pointer, right? Slap a star in front, and write the whole thing in brackets like that, right? So this reads pointer2, or ptr2, is a pointer to a function that returns void and has one int parameter. Right? I can make that pointer point to a function by writing and then the name of the function after it. Right? Third example. Here's the max function. Right? Max returns int, right? Has two int parameters. Right? So to take a pointer to that function, called ptr3, right? Return type, parameter list types, separated by commas, right? No names of the parameters. Right? Name of the pointer, right? Star to indicate that it's actually a pointer, right? So this reads as pointer3, or ptr3 is a pointer to a function that returns an int and has 2 int parameters, right? I can make it point at the max function by writing and max, right? If you had another function here that also, right? So if I put in a second function that has the same return type and signatures, right? So for example, min, right? Min, int x, int y, right? Implementation here. Right? So if I have another function that returns an int and has 2 int parameters, I can make ptr3 point to that function as well, right? So ptr3 equals and min, like that, right? And so this, right? So being able to point at a function, right, lets you, now gives you some ability to implement what looks like polymorphism in C. Right? So I can take a pointer and I can point it at any function that I want to, as long as the return type and the parameter types match. Right? So now I can choose which version of a function I want to run. Right? And that's a very powerful idea, actually. Here's a function that returns a pointer. So the syntax doesn't change at all. Right? It's still, right? Returns a pointer to a double, has a double as its input. Right? So ptr4, right? The syntax doesn't change. Return type here, right? Pointer to double. Parameter types here, single double. Name of the pointer here. Right? So this reads as ptr4 is a pointer to a function that returns a pointer to a double value and has a double value as its input. Right? I can make it point at make double by writing and make double. All right, now functions are allowed to take in pointers to functions as their as parameters. Right? So make int takes 2 ints, a and b, right? And then it takes a pointer, right? Pointer to a function that returns an int giving 2 ints, right? So here are my 2 ints, a and b. So I'm going to call the function that's pointed to by fp using a and b. Right? So the syntax that you use is as follows. Right? So I'm going to call the function that's pointed to by this pointer. Right? So I dereference the pointer. That gives me a function. How do you call a function? Round brackets followed by the parameters, or the arguments to the function. Right? So that syntax right there simply calls the function that's pointed to by fp with the values a and b. Right? Now that returns an int. Right? So I've got a pointer to I've got a dynamically allocated pointer to an int here. Right? So in other words, I've got an array of size 1, right? And I points to that array. Right? I can dereference I and store the value of this function in I. So if this function points to max, right? Then the value of I is going to be the max of a and b. Right? If this function points to min, then the value of I is going to be the value of min of a and b. Right? So if I want a pointer to this function, right, what do? Right? Return type is int star. Right? So there's the int star. What's the parameter list? It's int, right? Int, pointer, int, right? So down here, int, pointer, int, right? It doesn't matter what name you put here. You put whatever name you want here. Right? Similarly, down here, you can, if you want to, include parameter names here if you want in the pointer declaration, or you can leave them out. Right? And then finally, right here is the name of your pointer. Right? So this reads as pointer5 is a pointer to a function that returns a pointer to an int. Right? The function has 2 int parameters, and it has a pointer to a function that returns an int and takes 2 int parameters. Right? How do I call that function? Right? So I have a pointer to the function. Can I use the function to call the function? The answer is yes. Right? So how do you do it? Dereference the pointer. Right? So that gives me a function. Now call the function. Right? So I'm going to call the function with the values 5 and 10. Right? This has to be a pointer to a function that returns an int and takes 2 ints. Right? So pointer 3, that's my pointer to a function that returns an int and takes 2 ints. Right? Currently it points to the min function. Right? And so pointer 3 is going to point to min. Right? And so the value of x is going to be the min of 5 and 10. Right? So you're going to get 5 when you run this function, when you run this program. So that's how you create a pointer to a function. Any questions on that? You have to get used to the syntax. So you have to write a few of these before before you really understand what's going on. Right? And you can have very, very convoluted pointers to functions, right? Depending on what the inputs or the return values of the functions are. Right? So for example, you have a function that returns a pointer to a function, right? So in that case, the declaration of the pointer looks really weird, because in the front, you've got a pointer to a function that as the return type. Okay, so back to our stack implementation. If I want to print an element, right? We want our print function. If we want to print a stack, then I need to know how to print an element, right? So I'm going to ask the user to supply a pointer to a function that can print an element, right? Now remember what our element type is, right? Our element type is always, Our element type, what am I doing? Our element type is always pointer to void, right? So I need to ask the caller, right, for some function that returns void, right, and takes in an element, right, where the element is pointed at by some void pointer, right? If I want to, I can ask them for a function that takes in a const pointer, pointer to a const value, right? Because printing an element shouldn't change the element, right? So they need to supply the print function some function that can print an element, right? Which means our print function is going to ask the user for a pointer of this form, right? I need to ask the user for a pointer to a function of this type, that returns void and takes in a const void, takes in a pointer to a const element, right? So our pointer definition is going to look like this, right? PTR is a pointer to a function that returns void, takes in one void pointer that points at an element. Right. Now, you may not like this syntax, right? I certainly don't like this syntax, right? Users of your stack class probably aren't going to like this syntax, right? Or they might. It depends how long they've been programming in C, right? Eventually you get used to it. So what you can do instead is that you can provide a typedef, right? Which makes it a little easier to write variables of the pointer type, right? So I can define a typedef, right? Now when you define the typedef, the syntax is also strange, right? So the name of your type becomes whatever's in here, right? So the type print underscore elem func, that's a pointer to a function, right? It's a pointer to a function that returns void, takes in a pointer to void that points at a constant value, right? So that statement there simply says that print elem func is an alias for a pointer to a function passing const void star and returning void, right? And now people instead when the user of your stack class needs to define a pointer to such a function, right? They can write print elem func as the type of that function instead of having to write void star blah round bracket const void star, right? To free an element, right? You want to call a function that looks like the following, right? Now again, remember, our elements are just are represented as pointers to void, right? So to free an element, right? I need to call a function that takes in a void pointer to an element, and then frees that element, right? So you want a pointer of the form void, right, the return type, void star inside the round brackets, right, some pointer name here. Right, and again, instead of making people write this all the time as their type, right, you can provide a typedef, right? So free elem func is just an alias for a pointer to a function that returns void and takes in a void star pointer, a void pointer to an element. All right, so let's look at the modified stack class now. It's not class, I guess it's the data type. Right, so in the header file, right, I want any user of the stack class to be able to define a, to be able to provide to me, or the implementer of this, or to the stack object, right, a function that can print an element, right? So here's our typedef for print elem func, right? So print elem func, pointer to a function that returns void, takes in a const void star pointer, or a const void pointer, right? Pointer to a function that frees an element, right? So here's our typedef, right? Free elem func, that's just an alias for any pointer to a function that returns void and takes in a pointer to void as its element. Right? The rest of the header file stays the same. Right? Stack free now and stack print, their definitions now change. Right? So to free a stack, right, or to free a stack pointed to by S, right, I might, or the stack might have to free the memory allocated to the elements. Right? It might not, depending on how the user wants to, depending on what the user wants to do. Right? If the user wants to free the, if the user wants stack free to free the memory for each element, they pass in a pointer to a function that can free the element. Right? So if you read the documentation for the function, right, it says it frees the memory associated with the stack. Right? If this thing here is not null, right, then the memory for each element is also freed. Right? How is it freed? You pass the element to this function, right, and that function frees each element. Right? If this is null, then that the user is indicating to the function that they don't want you to free each element. Right? They're going to do it themselves later on. Right? Printing a stack. Right? I need to know how to print each element. Right? So how do I know how to print each element? I ask the user for a pointer to a function that can print an individual element. Right? So when I print the stack, right, I'm just going to iterate over the elements of the stack. Right? For each element, I call print elem to print the element. Right? Oh, sorry. So when you go and look at the implementation, I want to now, well, I'll leave this in for now. So let's look at the print function. Right? So here's our stack print function. Right? The user has to pass in a pointer to a function that can print an element. Right? It's not hard. Right? So so I'm gonna, I actually wrote this recursively. Right? So I'm going to call my recursive helper function. Right? My recursive helper function takes in a node or pointer to a node. Right? It also takes in a pointer to the function that can print the element. Right? The recursive implementation is straightforward. Right? So if the, whoa, sorry. Hey, here we go. Right? So if the node is null, we're done, so you don't do anything. If the node is not null, I'm going to print the element. Right? How do I print the element? I call this function. Right? How do I call this function? Well, it's a pointer to a function. So dereference the pointer. Right? Pass in the element that you want to print. Right? So remember, nelem, its type is pointer to void. Right? So you just pass in the pointer to the element that you want to print. Right? And then print the rest of the stack. Right? Where's free? Free. is here. Right, so here's stack free. Right, again, someone can pass in a pointer to a function that can free an element, right, if they want to. Right, so what do you do to free a stack? Well, I just go to each node. Right, if that function is not null, if that pointer is not null, right, then I have to free the element associated, the element in that node. Right, so I go from node to node. Right? If the pointer to the free function, I guess if free lm is not null, right? So in other words, if the user has supplied a function that can free an element, call the function passing in the element. Right? Again, how do you call the function? Dereference the pointer. That gives you a function. Call the function. Right? So that frees the element. Right? Don't forget to free the node. Right? Because it's the stack that allocated the node, right? It's not the user that allocated the node, right? That frees the element that's in the node or pointed to by the node. That frees the node, right? That frees the actual stack structure itself, okay? All right, any questions about pointers to functions and how to use them in a generic data structure? Okay. Oh, stack demo. I guess we can look at stack demo, although I don't think there's anything super interesting here. So stack demo is just going to, oh yeah, actually there is something interesting here. So if you want to use the stack class, how do you use it, right? So I want to use the stack class, I want to print out the stack data structure, sorry. And I want to print out the stack, right? I could write the print function myself, but whoever implemented stack did it for me. All I have to do is provide a function that can print an element, right? So I'm going to make a stack, right? The stack that I'm going to make is a stack of strings, right? So I'm going to push the strings 1, 2, 3, 4, 5 onto the stack, right? So push those onto the stack. Each time I'm going to print the stack, right? Now, to print the stack, I have to tell the stack how do I print out a string each time, right? So I need to provide a function that prints a string, right? So print string, or print underscore str, that's the function that prints a string, right? But the input to the function is a pointer to void, right? It's not a car star, right? Or it's not a pointer to car, right? It has to be a pointer to void because that's the way the stack is storing its elements, right? As far as the stack is concerned, each element is a pointer to void. Right? Now, if you've got a pointer to void, right, you can't use that pointer for anything except to do things like comparisons, right? So I can compare two pointers. I can check if the pointer is null, right? I can check if two pointers are equal. I can check if one is less than the other one. But that's about all I can do with it. I can't dereference the pointer, right? Because if you dereference a void pointer, right? Remember when you dereference a void pointer, you get the object that's pointed to. Right? But a void pointer can point to anything. So you can't dereference a void pointer without casting it to something so that the compiler knows what this thing is pointing at. Right? So to print the string that's pointed at by s, right, I can use printf. Right? But when I use printf, I can't write this. Right? So in other words, I can't pass in the pointer s directly. Right? Because the pointer s, its type is void, right? It's a void pointer, right? What you have to do is you have to cast the value instead, right? So let me rewrite this slightly. So I'm going to call that str. So I'm going to introduce another variable str. So when you're writing these functions, right, it's usually useful to create a variable and cast the incoming argument, right, to the type that you want. Right? So what do I want? I know s is a string, right? So in other words, I know its type is really car, is really pointer to car, right? And so what you can write is as follows. Right? So take the incoming pointer whose type is a pointer to void, or void pointer, right? Cast it to a pointer to car, right? store that in another variable store that in a variable str, and then pass str to printf, right? So if you want to be explicit about it, that's the way you should write it, right? But you cannot use s directly in this context, right? And you can almost, I don't think you can, well, I should say it, you probably can never use the void pointer here directly inside these types of functions, right? You certainly can't do it for print, because in order to use printf, you have to cast the pointer to the appropriate type. So if you run this, this actually works the way you expect it to. Right? Now, stack demo 2, that's the one that frees. Print a list. Oh, I guess there's also in a corresponding. Why is this list? These should be all stacks. Anyway, these should be free a stack and print a stack. I don't know why they're called. Do I actually call? Oh yeah, I actually do call these. All right. Anyway, that's fine. Oh wait, that's weird. Oh wait, I know what's going on here. Okay, sorry, never mind. So in this example, I'm going to make a stack. I'm going to push a bunch of lists onto the stack, right? So start out with an empty stack. I'm going to push 5 lists onto the stack. So here is where I make my lists, right? Here's where I push the lists onto the stack. Right? Now, if I want to print out a stack of lists, right, I need a function that knows how to print a list. Right? So here's my function called printList. Right? It takes in, as its input, a pointer, a void pointer, that actually points out a list. Right? List to string. Okay, so I convert the list to a string using list to string. Right? Now, the list to string, this doesn't actually work, right? I have to list, where's list to string? Oh, this does work. Where's list to string? So list to string, here we go. Down here. Right, now notice list to string takes in a pointer to list, right? But I can safely pass that a const pointer to void, right? So this turns out this works. So here I don't need the cast, right? So here I can actually safely pass this, and then when I pass the pointer to list print, right, the compiler will do the cast for me, right? So list to string will actually get a pointer to a list, right? And away you go, right? Now I can print the list, right? And then I can free the string that's returned by list to string. Right? If you don't free that string, right, you end up with a memory leak every time you print the list. Right? Freeing a list is the same thing. Right? So at the end here, when I free the stack, if I want to free all the lists that are also on the stack, I need a pointer to a function that can free a list, right, where the list is specified as a pointer to void. Oh, here's the actual cast. I think you actually need the cast up here. So I'm pretty sure you actually need that cast. I'll check this later on, but I'm pretty sure you need that cast. So here I'm going to free the list, right? How do I free the list? Well, the list data type provides a function that can free a list, right? It happens to have the right type, right? So in other words, it happens to return void, and it happens to take in a pointer to a list, right? So I cast t to a pointer to a list, right? And then call the list free function. When I call stack free, I pass in the address of the free list function. Right? So when you use the stack data structure to do something with the stack, right, to print or to free the stack, right, it's now up to the user to provide functions that know how to print individual elements or to free individual elements. Right? That's not actually asking the user for anything more than what they would have had to have done in the first place, though. Right? So if you didn't have a function that could print a stack, the user would have to write their own function anyway. Right? Okay, so there is a disadvantage to using pointers to void for implementing a generic data structure. right? So there's actually there's two big ones, right? There's two big disadvantages. So disadvantage number one, right, is that the elements now are, as far as the stack's concerned, right, the stack represents the elements as pointers to the elements, right, pointers to some values, right? And so that means your elements should have allocated storage duration, right? So in other words, they should be dynamically allocated, right, or have static storage duration, right? Right? Now, why is that true? Right? Because if they don't, right? So if you write a function, inside the function you've got a bunch of int variables, right? So int A, int B, int C, int D, right? You make a stack inside that function, right? Where you're passing, for the elements, you're passing in pointers to your local variables A, B, C, D, and E, right? You then return the stack back to the caller, right? So what's the problem? The problem is your variables A, B, C, D, and E, they don't exist after the function finishes running, which means that the elements that are pointed to in the stack, they don't exist either, right? So those void pointers that are pointing to elements, those are all nonsense now, right? So whenever you have, so when you use a stack data structure, or when you use any generic data structure where you're representing the elements as pointers to void, those elements need allocated storage duration, right? Which means you need to dynamically allocate the memory associated with them, right? The problem with dynamically allocated memory is it's slower than automatic storage duration. Right? Let me back that up once. So the problem with doing this is that in the int-based stack, right, we stored the ints directly in the nodes, right? So in order to get access to the int value, all you have to do is look at the node and you get the int value. When you're storing them as pointers, right, to get access to the element, you now have to dereference the pointer, then jump and find out what its value actually, to find the actual value of the int. Right? It turns out that takes more time than if you had just stored the int in the node in the first place. Right? It's, for a high performance application, it actually takes a lot more time. So it's not, or it can take a lot more time. So it's not a trivial price here that you're paying. The other problem is there's no static type safety anymore. Right? So when we made a stack where the elements, where the nodes stored ints, you could only put ints into the stack, right? If you're now using void pointers to point to the elements, you can put whatever you want into the stack, right? So this behaves now like Python does, right? So in a Python list, you can put whatever you want in the list, right? A function that takes in a collection as input. So a function that has a stack, right? You write a function, one of the inputs to the function is a stack, right? You have no idea, or the function has no idea what elements are in that stack, right? There's no guarantees, right, on what element types are actually in the stack, right? If the person that's using the stack is careful, right, so in other words, if they always put in the same element type, right, then there's probably no issues, right? If someone makes a mistake and puts in a double into a stack of int, right, now you've got a problem. Right? Because when you start to pop the elements or look at the elements in the stack, you don't know for sure whether or not everything's an int. Right? When you get to that double element, funny things happen. Right? So C, no type safety.c. Here we go. Oh, there's a lot here. What time is it? 2:14. Let's look at this in the next class, because we're not going to get through this all anyway in the next 5 minutes. And there's actually a lot here. So we'll look at the lack of type safety problem in the next lecture. Right? Any questions on implementing generic data structures? Hey. Anybody? All right. So I will see you Friday.